We all wake up to dark mornings, sweat through the heat of summer, and shiver in the cold of winter. These familiar, everyday moments are actually driven by events happening millions of miles out in space. It starts with the fact that the ground beneath our feet is performing two movements at once. Our planet is constantly spinning like a top, and at the very same time, it is traveling in a massive circle around the sun. That first movement is called rotation. If you imagine an invisible straight line running through the center of the Earth from the North Pole to the South Pole, that is our axis. The planet constantly twirls around it. Because the Earth is a solid globe, the sun's light can only hit one half of it at a time. The side facing the sun stays in daylight, while the side facing away sits in a dark shadow, giving us night. We call the boundary between the light and the dark the circle of illumination. Because the Earth spins from west to east, we physically sweep through that boundary every morning and evening. It makes the sun look like it's moving across our sky, but we are actually the ones turning past a stationary sun. When you measure a single day, you are simply counting the 24 hours it takes for the Earth to complete one full spin. That rotation provides the steady, reliable rhythm that dictates our daily lives. While 24 hours feels standard to us, rotation speeds vary wildly across the solar system. Jupiter is the fastest spinning planet in our neighborhood. Even though it is more than 11 times wider than Earth, it completes a full rotation in just 10 hours. That high-speed spinning physically affects the planet. Like spinning dough, rotation forces the Earth to bulge at the equator and flatten at the poles. Because of this, Earth isn't a perfect sphere. We call this shape an oblate spheroid. This means the Earth's rotation does more than track our time. The sheer physical force of the spin dictates the very shape of the planet we live on. Earth travels on an oval track around the sun. This revolution takes 365¼ days, 1 Earth year. As Earth orbits, its axis sits at a permanent 23.5-degree angle. That tilt remains completely rigid, pointing in the same direction into space all year. Many assume seasons happen because we move closer or further from the sun's heat, but we are actually closest to the sun in early January. Our seasons rely instead on that 23.5-degree tilt. As we orbit, the tilt determines which parts of the globe receive direct, intense sunlight, and which parts receive sunlight at a shallow, weaker angle. On June 21st, the northern hemisphere leans directly into the sun's rays, bringing the longest day, the summer solstice. By December 22nd, on the opposite side, the lock tilt means it leans away. Sunlight hits at a glancing angle, bringing shorter days and the winter solstice. Because of this fixed angle, seasons are exactly opposite in the two hemispheres. When North America experiences summer, the southern hemisphere tilts away into winter. Twice a year, in March and September, we reach the midway points on our track. These are the equinoxes, when the Earth's axis leans neither toward nor away from the sun. On these 2 days, the sun is directly over the equator. This distributes light evenly across the globe, making day and night lengths equal everywhere on the planet. These solstices and equinoxes are the astronomical markers that divide our calendar and govern the global rhythm of the climate. These powerful planetary movements drive our local weather patterns, like the heavy monsoons that define everyday life across India. From June to September, the shifting angle of the sun brings intense heat, drawing moisture off the oceans, creating a concentrated season of heavy rainfall. Once the Earth moves further along its orbit, that angle shifts, leaving the region dry for the rest of the year. This shift forces the people living there to adapt and find ways to store water. In places like Rajasthan, historical societies engineered massive stone stepwells to capture and conserve rainwater during wet months, ensuring a supply for the dry months. These ancient structures are a direct human response to the physical realities of the Earth's axial tilt and its journey around the sun. Finally, we have to account for that extra quarter day at the end of every orbit, which creates a discrepancy with our 365-day calendar. To fix this, we save those quarters. Every 4 years, they add up to 1 full day, which we add to our calendar as February 29th. Without this leap year correction, our calendar months would slowly drift out of sync with the physical seasons. The timing of a monsoon raindrop, the length of a noon shadow, and the dates on our calendar all follow the same mechanics of a tilted planet spinning and leaning through space.